Accurately predicting stroke occurrence is crucial for healthcare providers and patients. Early identification in a high-risk individual allows for timely intervention, potentially saving lives and reducing healthcare burdens. In this project, we built a classifier to predict strokes based on patient features using machine learning techniques. We evaluated multiple models, performed extensive feature engineering, and optimized the best performing models through hyperparameter tuning. Our objective was to maximize predictive performance while ensuring the model generalized well to unseen data. For data preprocessing and feature engineering, to improve data performance, we conducted comprehensive feature engineering. First, we handle missing values. We replaced missing values with medium imputation to ensure that no data was lost while maintaining the integrity of the data set. Secondly, we categorizing continuous variables. We categorize variables like age into meaningful groups, young, middle-aged, elderly, very elderly, to capture patterns more effectively. Similarly, BMI was categorized into underweight, normal, overweight, and obese. Thirdly, we transformed skewed features. Variables such as glucose levels and BMI exhibit skewness. So I applied log transformation to normalize their distribution and improve model stability. Fourthly, I created interaction features. To capture relationship between different features, I created new variables such as age BMI interaction and glucose BMI interaction, which helps models understand dependencies that might not be obvious from individual features. Fifthly, we generate polynomial features, such as squared terms for age and BMI were included to capture nonlinear relationships. Lastly, one-hot encoding categorical variables is used. Since machine learning models require numerical inputs, categorical value variables were transformed using one-hot encoding to ensure that all models could process them correctly. Um, we I also trained and evaluated multiple machine learning models to determine the best classifiers for stroke prediction. For example, I evaluate the random forest classifier, the gradient boosting classifier, the XGBoost classifier, and the LightGBM classifier. Each model were evaluated using stratified k-fold cross-validation to ensure that our model generalized well across different subsets of data. The primary metric for evaluation was F1 score, as it balanced precision and recall, making it suitable for imbalanced data set. The best model, according to our results, is the XGBoost. XGBoost outperformed other models due to its ability to handle complex features, interactions, and imbalanced data effectively. I got an XGBoost score of 0.9697. XGBoost used gradient boosting to optimize model performance, meaning it sequentially improves weak learners by minimizing errors in each iteration. Its ability to handle missing value internally, along with its regularization capabilities, made it the most effective classifier for the task. Then we applied hyperparameter tuning and model optimization for our XGBoost model. Right here. The learning to further enhance performance, we applied this technique, and instead of manually selecting hyperparameter, I used randomized search CV, which systematically explores different configurations to find the best performing set of parameters. The learning rate optimization ensured that the model learned at an optimal pace, balancing between underfitting and overfitting. Tree depths and feature sampling controlled how deep each tree grows and how much data each tree uses, preventing over complexity. Regularization parameters applied L1 and L2 penalties to reduce overfitting and improve generalization. The balancing training data, we adjusted weight parameters to address class imbalances, ensuring the minority stroke class received appropriate attention. To assessing and improving model fit, we analyzed feature importance. I identified which variables contribute the most to stroke predictions, and I also plotted the learning curve. Learning curve helped assess how well the model was generalizing by analyzing the training and validation performance over increasing sample size. I determined that the model was overfitting or underfitting. A large gap between training and validation performance suggests overfitting. whereas consistently low scores indicate underfitting. I also plotted the precision recall curve, which provide me with insights into how well the model balanced false positive and false negatives. Um, the performance improvements and final results is it's not really obvious after I did the hyperparameter tuning. By integrating advanced feature engineering, rigorous model selection, and systematic optimization, we still built an effective stroke prediction model. The use of XGBoost combined with hyperparameter tuning and performance validation allow me to develop a robust classifier that can assist in early stroke detection. This process highlights how machine learning can be applied in healthcare to enhance decision making, leading to better patient outcomes and optimized healthcare resource allocation.